Welcome to Fresh Thinking by Snowden Optiro. My name's Ian Glacken. I'm an executive consultant at Snowden Optiro's offices here in Perth. And today I'm joined by my boss, Susan Havlin, who's the managing consultant at the Geology Group. Welcome, Susan.
Thank you, Ian.
This is the fourth in the series of 7 podcasts. And the theme of this series is looking at estimation techniques in mining, looking at recoverable resource techniques in mining, and providing the solution to the issues, which is what we call localized conditional simulation. So we talked about estimation, we've talked about recoverable resources, we've talked about what conditional simulation is. Now we're going to bring it all together, and Susan's going to tell us all about localized conditional simulation in this episode. So Susan, what is localized conditional simulation?
I'm glad you asked that question. So localized conditional simulation is a technique that allows us to convert the results of multiple conditional simulations, or what we like to call realisations, into a single block model that preserves the realistic grade variability. So as we discussed in previous episodes, conditional simulation generates many possible realisations of the deposit, but each realisation honours the data and the spatial continuity of grades. But the location of the high and low grades between drill holes varies from one simulation to the other. LCS uses the information contained in those realisations to construct a single model that reflects the distribution of grades expected at the mining scale, so while still honouring the statistical properties of the simulations or realisations. So in essence, it allows us to combine the strengths of a simulation with the practicality of a single resource model.
Okay, so you've talked about this word localization, and we do need to explain what it is. So what is localization, and why do we need localization?
The main reason is the simulation produces many possible outcomes or realisations, while most mining workflows require only one model, such as what we do for an OK estimate. So mine planning tools, optimisation algorithms and reporting frameworks all operate on a single block model rather than a whole range of 50 realisations. So localisation provides a way to extract the information from the simulations and redistribute it into a single model that retains the realistic variability of the drilling data. So without localisation, it would be difficult to use the simulation results directly in most planning and reporting workflows. Near on impossible, really.
Right. So essentially we're taking 50 or 100 realisations of grade and we're turning it into a single block model. So how exactly does that process work?
So the process begins by generating these multiple realisations, like whether we do 50 or 100 or whatever number you decide. So these simulations are typically created at a point support, which represent grades at a very small scale. So it would be smaller than your SMU. So one thing to note is that it's easier to simulate at smaller scales without suffering from over-smoothing, as you might see in kriging, for example. So when you look at the grade distribution at the point scale, simulated point scale, you note that it nearly exactly replicates the background grade from the drill hole data.
And that's one of the benefits of simulation. It doesn't suffer from smoothing or conditional bias to the same extent as kriging.
Yeah. So the simulated grades are then regularised to the selective mining unit, or the SMU size, which represents the smallest unit that can be realistically mined. So once the simulations have been converted to the SMU support, localisation is applied using a panel to SMU approach. So in simple terms, the grade distribution from the simulations at the panel scale is redistributed to the SMUs within that panel. Now, what size panel you choose depends on your deposit and your drilling, but the ordering of the grades is guided by what we call the E-type estimate, which is generated when you generate 50, 100, 200 realisations. So this is the average grade across all the simulations generated at that SMU level. This process preserves the overall grade distribution from the simulations while producing a single block model that can be used for planning and reporting.
Right, you just mentioned that word E-type. Can you just explain exactly what it is, just simply?
Yeah, so simply an E-type estimate is actually the average grade across all of the realisations at each location. So if you generate, for example, 100 realisations, you can calculate the mean grade at each block or SMU. So that mean value is what we call the E-type estimate. So in the localisation process, the E-type values are used to rank the blocks or SMUs within that panel that we've chosen, which helps determine how the simulated grades are distributed when constructing the final model. This ensures that the local ordering of grades remains consistent with that expected from the grade distribution.
Right, so we've got this localization process. We've taken our simulations, our realizations, and created that. So once we've got the outcome of that process, which is an LCS model, what does it look like compared to, say, an ordinary Krieg model?
Well, the most obvious difference is the grade distribution. When you plot up the localized grade from the localized conditional simulation against your input drill hole data, you see that it doesn't exactly reflect it, because obviously we've changed the size of the block from the point up to the SMU, but it does replicate that grade distribution. And because kriging tends to smooth the grades, the resulting block model often shows like a narrower range of values, whereas the LCS tends to still replicate the range that is coming from the drill hole data. So in the ordinary Krieg model, the high grades tend to be reduced and the low grades are increased, which compresses this distribution, while in contrast, the LCS tends to retain much more of that natural variability captured by those realisations. So when you compare the grade distribution, the LCS model tends to match the distribution observed by the composites more closely than, say, an OK model would.
Yes, so another one of the underlying issues with this is that one of the assumptions is that we're not able to estimate using kriging directly into SMUs. So what we're doing with this technique, which we're describing, is we're coming up with an SMU estimate using the process of localization, and also using the techniques of simulation. So essentially we're talking about recoverable resources here. And remember we spoke in the earlier episodes about MIK and UC, uniform conditioning, and MIK. So how does this LCS technique actually relate to recoverable resources?
That's a good question. It relates very directly. So the recoverable resource methods aim to estimate how grades behave at that SMU scale, rather than simply predicting like a bigger block average grade. So the localized conditional simulation achieves this by using simulation to capture grade variability and then redistributing that variability at the SMU scale. So the resulting model reflects a grade distribution that is much closer to what would actually be encountered during mining.
Okay, so the industry is using localization with other techniques such as uniform conditioning or multiple indicator kriging. Can you explain the origins of this localization approach?
Sure, yeah, because it's not new. Just like the conditional simulation, we're not creating a completely new concept. All we're doing is combining conditional simulation with this localization. So this approach was originally described by Absalov in 2006 and has been used in methods such as localized uniform conditioning, which is a way of translating panel scale recoverable resource estimates into block scale models. So it's been used with MIK using exactly the same approach as with uniform conditioning. So what's different with the localized conditional simulation is that the localization process is applied directly to the realisation results, which means the resulting model preserves the variability captured by these realisations.
So in essence, what you're saying is we get the advantage of localization, which takes a panel estimate, turns it into an SMU estimate, but we also get the benefits of simulation.
Yep, exactly.
So why do you think this is important, and why is there interest in this approach?
I think, it relates back to why people are using conditional simulation. So there are a few reasons, but first, obviously, is our computing power has improved, and software tools have made it like significantly easier and making simulation workflow much more practical. Secondly, there's an increased recognition that the grade variability and the uncertainty, as you say, can have a significant impact on mining decisions.
Okay, so in this episode, we've talked about the algorithm itself, localized conditional simulation, and as Susan's just explained to you, we've discussed this dual feature of this algorithm, which gives us a grade estimate, if you like, an SMU estimate, which is what we require for mine planning, but it also gives us the variability in grade, which simulation gives us. In the next episode, we're going to talk about the variability side of things and what we can get from that. So thank you very much, Susan.
Well, thank you, Ian.
I hope you enjoyed that episode of Fresh Thinking by Snowden Optiro. If you enjoyed that, please subscribe, and you can find it where all good podcasts are found, including our YouTube channel. Thank you.